Molweni sanibonani shafere kunjani. I go by the name of Motizo. Welcome back to the YouTube channel Yamanyora. How to kale pansola, please subscribe, hit the bell notification and hit that like button. So today we're going to Pascal. So we're going to deal with Pascal's law. So this law states that the intensity of pressure at any point in a liquid at rest is the same in all directions. So we'll prove that idea. Let's get it. As indicated earlier, on this lesson, we're going to deal or discuss Pascal's law in static fluids. Before we commence, let's start here. So we know the static pressure is equal to force over area. So force is equal to pressure multiplied by area. So now, there are a few things or a few points that I want to make before we get to the crunchy stuff. So in pressure in liquids, we know, or we need to be aware that forces at any point in a static fluid or fluid at rest acts perpendicular to the surface at that point. So it acts normal, or you can rephrase it and say it acts at right angle to that phase. So forces at any point in a fluid at rest acts perpendicular to that surface. The second point is pressure at any point in a static or at a fluid at rest is the same in all directions. In fact, that is what we're going to prove in this lesson today. So now, let's go down a little bit. So we're going to prove that a pressure at a depth in a static or a fluid at rest is the same in all directions. So let's consider a small fluid element. So it's so small that in other literatures, when you're reading through it, it will be labeled the length dy, dx, dz, right? So we have the x, y, z plane. So this prism-like element has lengths mo, ot, and tm. So these are the lengths on the prism. So we're also aware that angle MOT, which is this angle, is equal to theta. That's the angle. So firstly, let's compute or let's look at the forces in those three different phases. So consider the pressure at a surface, at the length or at the surface, this surface. So OTS is being equal to P1. So the pressure or surface TMS is equal to P2, and the pressure on MOS is equal to P3. So when we compute or we want force in those phases or on those surfaces, so force on the phase OT, which is this one, OT, is equal to P1 times OT times S, which is the thickness or the thickness of the prism, right? So this is the pressure multiplied by OT by S is the area. So this is the force on this phase. When we move to this phase, the bottom phase, you see force is equal to P2, which is the pressure, multiplied by Tm, which is this length, multiplied by the thickness S. And the same is true on this phase, where you have P3, which is the pressure, multiplied by the area, MO or OM, multiplied by S. So those are the forces on those different phases, right? So what I'm going to do now is going to zoom in, because you can see here P3 is acting at an angle, but it's perpendicular to this phase. But when you compute for vertical and horizontal forces, you need to consider the vertical component of that force and the horizontal component of that force, meaning you'll be having an angle or a triangle like this, and this angle here, it will be equal to theta, this one. So you're going to compute for the vertical component, which is this one, and this one, which will be the horizontal component. Right. We'll deal with that later. I'm going to zoom in that angle. So when you zoom in that triangle, so you got the triangle MOT, right? So MOT. So angle MOT is equal to theta, which is this angle. Let's go a little bit up. So angle MOT is equal to theta. All right, that's the angle that we're dealing with. So now, when you want the vertical component of this P3, you know sine is equal to opposite over hypotenuse. So now, what's our opposite length? Our opposite length is MT or TM here over MO, which is this length, MO. So meaning Tm is equal to MO sine theta. So this is our vertical component of that force. So now our horizontal component, we know cosine is equal to adjacent over hypotenuse. So adjacent is TO divided by MO. So now we can say TO is equal to MO cos theta. Right. So now let's move a little bit downward. So we know this this fluid is at rest. That's the other thing. And this element that we're considering is so small that we assume that is on the same height. That's how small it is. Remember, in fluids, pressure increases with depth. So if the depth or the height from the surface of the water changes, it means the pressure changes. So we consider this element of the fluid so small that we assume this fluid element is on the same height. So I wanted to clarify that. And the other thing, we assume that the object is in static equilibrium. So opposing forces are balanced, right? So what we want to prove is we want to prove that the pressure intensity at a fluid at rest is the same in all directions. What does that mean? That means P1 is equal to P2, which is also equal to P3. That is what we want to prove, right? So let's go down a little bit. So we know the object in static equilibrium, the opposing forces are balanced. So therefore, that simply means the sum of vertical forces and horizontal forces equal to 0. So moving forward, when we look at this this fluid element, so what are the vertical forces? The vertical forces would be P2, which is P2, this one, multiplied by Tm, which is this length, Tm, and then multiply by the S, which is the thickness of that fluid element, multiplied by S, is equal to, because remember we assume, let's go down a little bit, we assume that the upward forces to be positive and the downward forces to be negative. So when you look at P3, it's going on the downward direction. So it will be considered a negative. So we would have rather said P2 Tm by S is equal to or minus P3 sine theta OM multiplied by S. So we just move the P3 on the other direction, right? So P2 Tm by S is equal to P3. So we want the vertical component of P3, which is MO sine theta. So P3 sine theta is the vertical, this part is the vertical component of that one. Remember P3, this one, is equal to MO. So P3 is equal to MO, this length. So it was going to be P3 sine theta, which is the vertical component of that force, multiplied by, where is P3 acting? On this surface. So it's going to be MO multiplied by S, right? MO multiplied by S, which is on the surface. That's the area on that surface. So it's MO multiplied by S, force on that surface. Right, let's move down a little bit. So when you look here, sine theta multiplied by OM, which is the vertical component. Sine theta, which is this one, multiplied by MO is equal to TM. So sine theta by OM is equal to TM. So you know TM cancels this TM. You are only left with the thickness, then the thickness cancels out. So we prove that P2 is equal to P3. Right. Let's move down a little bit when we consider the horizontal forces a little bit. So then again, we assume forces going to the right to be positive and forces going to the left be negative. So the force that is going to the right here on this face is P1. So the forces on this surface TO or OT is P1 multiplied by OT multiplied by S, which is the thickness, which is this one, P1 TO by S. And then P3 cos theta is the horizontal component of this pressure. So it's P3 sin theta multiplied by the thickness, multiplied by the area, sorry, MO by S. So which is this one, MO by S. So now let's go down a little bit where we zoom the angle. So how much is TO? TO is equal to MO cos theta, right? So let's go down a little bit. So we have TO, we have MO cos theta, which is equal to TO. So this value, which is equal to TO, cancels the TO, and then the thickness cancels out. So now we know P1 is equal to P3. Therefore, P1 is equal to P2 is equal to P3 because P3 is equal to P2. So now, what we just done, we just proved that the pressure density at any point in a liquid at rest is the same in all directions. I go by the name of Mortis. I'm out. Ula Sivi.